Our next speaker is Howard Herzog, who's a senior research engineer at MIT Energy Initiative, and he will be talking about the role of carbon capture and negative emissions. Please join me in welcoming him to stage.
Thank you. It's a pleasure to be here. I'm going to talk about climate change and the role that carbon capture and negative emissions can play in it. Fossil fuels is the basics of the world energy supply. It's over 80% of our supply. And even though we've been trying to decarbonize for a decade or two, we're not making a lot of progress. A lot of reasons for that, and a lot of it's with the policy. But basically what we do today is we take the fossil fuels out of the ground, we burn them to get energy, and we put the emissions, including the carbon dioxide, into the atmosphere. That's carbon positive. It puts CO2 in the atmosphere, which contributes to climate change. What carbon capture and storage does, it can make this process carbon neutral. By that I mean we take the fossil fuels out of the ground still and burn it, but instead of putting the emissions in the air, we capture them and put them back down into the ground. So that's the basis of carbon capture. Negative emissions takes it one further. It says, let's grab the carbon out of the atmosphere and put it into the ground. So I'm going to talk about some technologies that can do that and where they are and which looks the most promising. I wrote a book on the subject of carbon capture about a year ago, and so if you're interested, you can read about a lot of the topics. Today, I only can focus on a small section, and that, once again, is going to be the negative emissions. So people use the term deep decarbonization, but really what we want to do, what we have to do, is get to stabilization, which means we can't put more carbon into the atmosphere, or any carbon we put in, we have to offset it by taking some out. So that's what people call net zero emissions. The problem with trying to decarbonize or get the carbon out of all of our energy systems, our transport systems, our electricity systems, our industrial systems, is that about 30% of these emissions are just either hard to decarbonize or very, very expensive. Here we're looking at all greenhouse gases, so there are emissions that come out of agriculture and livestock too that are in here. So how do we do this? And the idea is to use negative emissions to offset them. So we still let these emissions go in the atmosphere, but we offset it by taking some out. And the last couple of reports from the Intergovernmental Panel on Climate Change, the IPCC, really highlighted negative emissions. And there's been quite a lot of papers and a lot of work and companies starting in this field. So what are the pathways to negative emissions? You can look in the literature, and there's lots of different ways to categorize these pathways. But I categorize them in 5 categories, and some of these have subcategories. The first on there is terrestrial and biological. This is the most straightforward. It's one, we're doing things today in this area, and this is as simple as reforestation, planting trees, for instance, but it covers much more than that. It also covers changing some agricultural practices. It covers storing the carbon in the soils. The next two, mineralization, which is basically turning the CO2 into rock, which nature does, by the way, but takes nature hundreds of thousands of years to do this, and storing the CO2 in the ocean. These are both highly speculative. There's a lot being written about it, but I haven't seen anything there that's a real pathway forward, in my opinion. The last two deal with carbon capture and storage, basically taking the CO2 out of the air and putting it in the subsurface in these geologic formations. Direct air capture is done using an industrial process, and I'll show this in a minute, an example of this, where the process removes the CO2 from the air, and then you can put it in the ground. The bioenergy with CCS or BECCS, what that does, it lets trees or lets grasses, different energy crops, pull the CO2 out of the air. Then we burn the biomass, just like we'd burn coal or oil at a power plant. We'll capture the CO2 from the flue gas and put that into the ground. So these are the two pathways I'm going to focus on. So let's start with direct air capture. There's been a lot of press on direct air capture in the last couple years. It's a very seductive concept. We can have these machines sitting out there cleaning our air with CO2 and will let us continue to put the CO2 out of our tailpipes of our car, out of the smokestacks of our industry. It's a very seductive concept, but unfortunately, it's sort of a mirage. We can do it. The question is not whether we can suck the CO2 out of the air, but what's the cost? And so there are several companies that are out there that are trying to commercialize this, and they put out cost numbers that, to be kind, are just not credible. Numbers they're putting out are in the range of $100 to $200 per ton of CO2 captured. I've done a lot of work on this. I've been following the area for about 10 years and analyzing it. I've analyzed whatever they put out in the public, and I still firmly believe that the cost of doing this is going to be on the order of $1,000 per net ton of CO2 removed. Now, I use the word net because it takes a lot of energy to take the CO2 out of the air. So most times you'll be putting CO2 up from that energy use. And so what you're really interested in is not how much you take out of the air, but how much you take out of the air minus how much you put in the air during the process. So let me put this carbon cost in perspective. Where I come from in New England, we have something called RGGI, the Regional Greenhouse Gas Initiative. And that's put a price on carbon for certain segments such as power plants. And that price is generally under $5 a ton of CO2. Fairly small, really not having a big impact on consumer cost or anything. In Europe, they have a trading system. And for the last couple years, the price of their carbon permits in their trading systems runs about 20 to 30 euros per ton of CO2. A lot of studies show that you can decarbonize electricity systems on the order of between $50 to $100 per ton of CO2. So something that's going to cost $1,000 per ton of CO2 really isn't going to get adapted very much in the next few decades, and maybe not even after that. And why is this so expensive? And the answer is concentration matters. The cost of capturing CO2 from a gas basically correlates very well with how concentrated it is in that gas. So when you look at CO2 coming out of power plants, like a coal-fired power plant, it's about 12% concentration. In the atmosphere, it's 300 times more dilute, or 0.04%. In other words, 400 ppm in the atmosphere. And this has great impact on both capital and energy costs. I'm going to give, first I'll do a little thought experiment about this. So imagine you have a big container and it contains 4,000 marbles. Of those marbles, 400 are blue and 3,600 are red. And they're all mixed up. And you want to pull out the blue marbles. Those blue marbles are the CO2 molecules. The whole thing represents a flue gas from a power plant. So you can do it. It's not so bad. But let's look at the same analogy with air capture. I still have those 400 blue marbles. But now the total number of marbles is 1 million. So almost 1 million red marbles with only 400 blue marbles scattered throughout there. Now you've got to pull out those blue molecules. It's going to take you much longer, more energy, much harder. So this is the task and why direct air capture is so expensive. Another thing, because of that factor of 300, you have to process 300 times as much air to get out the same amount of carbon as you process in a flue gas. So this is a picture of a carbon capture plant at a coal-fired plant outside of Houston, Texas, the Petronova plant. it captures 1.6 million tons of CO2 a year. What I've circled is the area where the carbon capture plant is, and that big tower you see there is the absorber tower. That's where a chemical, an amine, contacts the CO2 in the air, and you have a chemical reaction, and the CO2 goes into the amine. The rest of the plant then regenerates the amine to release the CO2 and bring it back. You do that through what's called a temperature swing by heating up the amine. So get a feel of that size and remember it. This is an air capture plant. This is from Climeworks, a company in Switzerland, and this does 900 tons of CO2 a year. You can see those are all fans on the front of this unit to push the air through. And you can see very different aspect ratio, a much skinnier unit, and that's all due to the difference in concentration. But to do that same 1.6 million tons a year, you need 1,800 of these units. So that is quite a bit. So let me show this in another way. So what you have in these units, you have to put so much air through, you put it through at a certain velocity. For these absorbers, that velocity is almost always in the range of 1 to 5 meters per second. You have to take a certain percentage of the CO2 out of there. This shows a range between 50 and 90%. And this company, Carbon Engineering, another one of these startup companies capturing CO2 out of the air, published some specs on their plant, and they run at 1.5 meters per second and capture 75% of the CO2 emissions. That means they need an absorber with a cross-sectional area. So look at a big wall that's 10 meters high, about a 3-story building, by 5 kilometers long. And that's just to capture 1 million tons. Now, 1 million tons is not going to do you much good. You got to get up to billions of tons. And of course, you're not going to have a single wall. You're going to have to separate this. You have to pipe between it. And this starts really rising the cost. So these are all sort of why I think these costs are very expensive and going up to about $1,000 a ton. Now, bioenergy in CCS is very different. We use energy crops. So the crops, whether they're woody biomass, like trees, or the grassy biomass, like switchgrass, pull the CO2 out of the air through the process of photosynthesis. So we don't need those big absorbers to grab the CO2 out of the air. Then we burn the biomass, we harvest the biomass and burn it in a power plant. And we produce energy. That energy not only drives the CO2 capture process, so we don't need excess energy for that. It has excess energy to produce electricity as a byproduct, which we can sell. And this electricity as a byproduct is carbon-free electricity. Now, there are issues, and those issues revolve around land use change and the biomass supply chain, and I'll talk about those in a slide or two. So what's the status? Well, there is no large-scale bioenergy CCS plant in operation today, but the two major components are in operation at large scale. So there's the Drax power plant in England. This produces 2.6 gigawatts of electricity. It actually gets most of its feedstock from the United States. So in the southeastern United States, they pelletize wood, and then they take it by ship and bring it to the power station in England. In terms of carbon capture at power plants, capturing from biomass plants almost identical to capturing from a coal plant. I showed you the plant in Texas, the Petronova plant. There's another plant operating at the 1 million ton per year scale up in Canada in Saskatchewan called Boundary Dam. So these things exist. And what we've done at MIT, we've done a recent study. We're in the final midst of submitting a paper on it. We use our big energy economic model and look at the issues of biomass and CCS and see what impact this can have on dealing with climate change. We include all the technical and economic parameters, from looking at land availability to the biomass transport and production and transport, to its conversion and production of electricity, to the capturing of the CO2 and injecting it into the subsurface, and also looking at land use changes and the carbon emissions associated with those land use changes. The results are here. The blue, this is for a scenario where we stabilize at 2 degrees C. This shows the carbon price, and without bioenergy and CCS, we see the carbon price raise significantly up after 2050 and actually go above $2,000 per ton by 2100. Whether people are really going to pay that type of price is highly questionable, but this is what the model says if we really want to stabilize at 2 degrees C, which is the goal of the IPCC and the Paris Accords. So, as I said, there were this group of technologies that are very hard and expensive to decarbonize, and that's what's driving the curve up. But you see the green curve. That's what happens if you have bioenergy and CCS. And that basically says the bioenergy creates negative emissions, so we don't have to reduce the emissions from those other things. And we can do this at a price of about $240 per ton of CO2, a much more affordable price and a price that may be acceptable. Other things in the model results, a little typo in here, that should read 30 exajoules in 2050, 320 exajoules in 2100. The total amount of energy the world uses today is on the order of 600 exajoules as comparison. And by 2100, the bioenergy and CCS is creating about a little over 20 gigatons, billion tons of CO2. That's a little over half the amount of carbon equivalent of greenhouse gases we emit today. People were always nervous about BECCS because they say it's going to really drive up food prices because of the land use. The model's coming back, and we were quite surprised by this. It's, people thought it would double or even triple food prices. It's only changing food prices by about 5%. So there is an impact, but it's very minor considering to the benefit we get by dealing with climate change. The real critical thing here is land use impacts. And the thing is, the model does not consider ecosystem impacts and social acceptability. These can and probably will limit the bioenergy and CCS, so you probably won't get as much as the model says we can get just based on technical and economic considerations. But some of these ecosystem impacts can be mitigated by regulations. And forests, for example, can be maintained for multiple purposes. You can harvest forest for the wood crops, for biomass, at the same time keeping them open for recreation, and at the same time ensuring biodiversity. So these are not mutually exclusive things, but they will take some management, and I think there's research in how to do this well. So I'm going to end with 3 takeaways. 1, negative emissions are extremely important if we're going to stabilize our concentrations of greenhouse gases in the atmosphere, which is what eventually we're going to need to do if we're going to get a handle on climate change. Direct air capture is very expensive, and that's due to how dilute the CO2 is in the air. And because of that, there's thermodynamic reasons, which I didn't go into as part of my talk, that's going to make it very hard to significantly reduce those costs. And finally, we think of all the negative emissions that bioenergy with carbon capture and storage, or BECCS, has great potential. The big if is we need to develop a sustainable biomass supply to feed this and to generate the negative emissions. Thank you.